we're happy to have Dorsa Sadig here today from Stanford. So just a brief bio on Dorsa. She's an assistant professor in computer science and electrical engineering at Stanford. She does research in robotics, learning, control theory, human-robot interaction. And specifically, she's interested in developing algorithms for safe and adaptive human-robot interaction. She received both her bachelor's degree and her PhD from Berkeley. And she's received a bunch of awards, including NSF Career Award, the AFOSR Young Investigator Award, the MIT Technology Review Under 35 Award, Google Faculty Award, Amazon Faculty Research Award. So anyway, it's very exciting to have her here, and she'll be talking to us about learning human models from non-traditional sources of data. All right, so thanks, Dorsa.
Thanks for the kind introduction. And yeah, Stephen and Pascal, thanks for having me here today. Really excited to be here and sharing some of our recent work in the space of learning from non-traditional sources of data. So in general, just a quick background, the type of things that I'm interested in is mainly focused on the algorithm design side of things for robotics, but for building robotics agents and AI agents that can better interact, coordinate, and collaborate with people. And today what I want to talk about is a little bit different from kind of the common themes of things that I usually talk about. Today I want to talk about learning from interaction data, and specifically learning from non-traditional sources of data. So this is a new talk, so bear with me. Slides are not like super like fine grained yet, but like we can go over it together and talk about it together. And again, yeah, feel free to ask any questions. I'm not monitoring chat, so if you have any questions, just feel free to speak up. All right, so why are we interested in this? So about a year ago, we started working on this problem of assistive feeding, which is a problem that's really like close to my heart, and I'm very excited about it. It's a very interesting robotics problem. You're thinking about picking up various types of food, deformable objects. It's an interesting interaction problem. We are thinking about how to transfer the food to a person's mouth. What should be the right forces that we put in? Like, how should we think about that transfer? Like if you have a force torque sensor at the end of this fork. And what I'm showing here is a baseline, which is following a fixed pose policy. So this is what is in the literature for how we should go about assistive feeding, following a fixed pose policy, doing motion planning, and following this trajectory, which kind of seems very uncomfortable, right? Like I think this user was very nice to us, who like didn't leave after this run. It's a very uncomfortable thing, and as you can see, like the robot is like pushing towards the person's mouth, not comfortable, not safe in any ways. It's not the best strategy that you might want to use. And at this point, we thought, okay, maybe we should try to use ideas from learning, and maybe that will help solve this problem. The quick answer is it doesn't currently in the space of assistive feeding, but I want to kind of like talk about our thought process. So our thought process was maybe we can collect some data of how a person maybe feeds themselves or feeds someone else. And maybe based on those demonstrations, maybe we can try to like do imitation learning and try to figure out a policy. And it turns out that expert demonstrations here is extremely limited. So like we need a lot of data to actually be able to have a very good feeding policy. And on the other hand, you might also think about reinforcement learning, and why don't we use reinforcement learning? And for this particular task, like as you can see, it's a very safety critical setting, right? Like I don't really want to get reward signals of hitting the person's face. Like I don't want that to be my reward signal to be able to use reinforcement learning here in this domain. And you might say, well, why don't we go into simulators? And we don't really have good simulators of a person's mouth or like even like the food objects that we are looking at. So this tends to be a very difficult problem. And at this point, we were thinking about, okay, so but how is it that we as humans learn how to feed ourselves? So how does a child like learn how to eat? And the first thing that might come to our mind is expert demonstrations, right? Like, of course, like we'll have expert demonstrations. We'll have a parent who'll like teach us how to pick up a bite of spaghetti and bring it to our mouth. Or maybe like the parent does kinesthetic teaching, actually like moves our arm or shows us some expert demonstrations. And I do agree there's a lot of value in expert demonstrations. I do agree that a lot of times we rely on expert demonstrations. But the thing that I'd like to argue in this talk is that sometimes we go beyond expert demonstrations. And there are many other sources of data present outside of expert demonstrations that we could actually tap into and leverage when we are thinking about these tasks. So for example, like when you think about this task of feeding, right? Like a lot of times we observe other suboptimal agents, and by just observing them, right? Like we realize what is the right strategy and what is not the right strategy, or what we should try next. So we shouldn't we should really like think about the fact that we have a lot of suboptimal agent data, and that could be potentially beneficial for a lot of these tasks. In addition to that, like sometimes you rely on our own unstructured play, right? Like children like tend to like play with their food. And if you think about that play is going to give us a lot of information about the dynamics of the food, about like how to pick up the food. And that is quite a bit of information that has quite a bit of like state action coverage that we wouldn't normally get from an expert demonstration or from just by observing other people. So I do think in general, like we rely on unstructured play fairly often. And another category of data that I'm going to talk a little bit about today is this idea of comparisons, right? There's a difference about like a perfect bite and like a bite of spaghetti that's slippery and the spaghetti is falling off it. And we could make those comparisons, right? Like we can think about which one is better and which one is worse and why is one better than the other. And those types of comparisons, pairwise comparisons, rankings, those are also sometimes like really like powerful sources of data that could teach us how to do various types of tasks. So in summary, like in theory, we might think that expert demonstrations is the only thing we rely on, but in practice, we end up relying on many other sources of data beyond expert demonstrations. And in this setting, I'm just mentioning a few of them: suboptimal demonstrations, unstructured play, and comparisons. There are, of course, other sources of data that we often rely on that I'm not talking about in this talk, but I just want to like mention a couple of them. And thinking about the task of robotics, like thinking about the task of like being able to feed a person, like this task has also a lot of similarities, right? Like we can't collect expert demonstrations. Like it turns out that for a lot of the robotics tasks, expert demonstrations are very difficult to collect, and they're very limited. Like we often use like various modalities like VR or joysticks or various types of devices to provide these data, and like through teleoperation or again through kinesthetic teaching. And that ends up being pretty difficult to collect as we've seen in a lot of prior robot learning work. And similarly, what ends up happening is that, well, if it is difficult to collect expert demonstrations on a real robot, well, we end up like relying on simulation, or we end up relying on data that comes from different tasks, domains, or morphologies. And sure, those are useful, but then we have to like worry about the transfer problem. So in robotics, right, like we have this problem of having access to very limited data. And similarly, I think we can try to tap into other sources of data, non-traditional sources of data, to try to better learn how to do these various types of tasks. So similarly, today I'd like to talk a little bit about how we can go about learning from suboptimal demonstrations that are not perfect, or how we can tap into unstructured play and how play data can give us like a lot more state action coverage. And if I have time, and I don't think I would have time, but if I have time, I'm going to talk a little bit about this idea of learning from pairwise comparisons. So this is a direction that we have been working on for the past like 4 or 5 years in my lab. We have quite a bit of work on this. So I want to talk about something new, and these two directions are fairly new. So I'm going to spend some time talking about these new directions, and then at the end, if I have time, I'll start talking about pairwise comparisons a little bit. All right, so that's the plan for today. So let's just get into it. So we want to talk about learning from a mixture of demonstrators with varying levels of expertise. And that's kind of the first section. Okay, so the setting we are looking at, let me just remind you, it's kind of this offline setting where we assume that, well, like in general, like in the offline settings, we might assume that we have access to an expert demonstrator or a robot policy that is somewhat expert. And then based on that, we are collecting data sets and we can do offline learning. We can either do imitation learning or we can do offline reinforcement learning. But we have some differences here. So first off, we are assuming that we are in an imitation learning realm of things, where we assume we don't have access to any reward functions. So we don't have any reward signals. We're not like in the offline RL setting. In addition to that, we're not assuming access to the environment dynamics. So I can't just do rollouts. I can't like try out things and do rollouts. So the only thing I have access to is this offline data set. And based on that, I would like to be able to go and learn a policy. The other thing is that we are assuming access to suboptimal demonstrators, as I've been mentioning. So we might have different types of agents with various levels of expertise. Like I might have a novice player or an intermediate player or an expert player. And all I have access to is their data set and who the data is coming from. So that is the setting that I'm in. And given that, I would like to be able to learn an imitation learning policy from these suboptimal demonstrations. All right, so how can we go about that? So what is expertise? So let's maybe talk about expertise for a second. So I'm going to refer to expertise as this parameter rho, and I'm going to just treat it as a number for now. And this parameter rho is going to tell me how good of an expert am I going to be in various types of tasks. So it should capture how skilled someone is in a given scenario. So you can think of rho as probability of succeeding in a task. It's closer to 0 if you have a novice player. It's closer to 1 if you have an expert player. Okay. And in general, this rho, we can think of it as something that is scenario-based or state-based. But for now, let's just treat it as a single number. That depends on the identity of our user. So a scenario might be that we have different shapes of different colors, and maybe our goal is to identify the color of a given shape. So I'm going to give a very abstract example just to talk about how the algorithm works and what we are trying to do. And then I'm going to lift it to the robotics domain or to domains that we are interested in. But for now, let's just talk about this very abstract problem. So maybe our goal is to identify the color of a given shape. So this is what we have. And maybe an expert comes in and says, well, it is red. And maybe a novice player says, well, that is brown. And we have possible states of different shapes and colors, and correct actions is providing the right color. So that is the setting that we are in. So if I assume I have access to the expert ground truth labels of expertise, so if I have access to the true rows, which are kind of identifying the expertise of my agents, the question is, what can I do under that scenario? In practice, I don't have access to these ground truth labels, but for now, let's assume I have access to these ground truth labels. Okay. So let's say that these are my states. My novice player has expertise of 0, so is going to get all of them wrong. My intermediate player is going to get 20% of these right, so it's going to get the red circle right. I have another intermediate player who is going to get 60% of these right. And let's say I have an expert who is getting all of them right. Okay. So one strategy that I can do here is I can do majority vote, right? Like I have a bunch of data coming from a bunch of a data set of a bunch of people, right? And I can basically take the majority of these actions and come up with a policy that says, well, given this particular state, these are the things that you're going to do. And the majority vote is going to do fairly well, except for this last bit, right? It's going to think that the color of this black circle is brown. And the reason it thinks that is it is taking majority vote. And I have a novice player and an intermediate player who are going to say, well, it is brown. And if I take the majority, I'm going to really like heavily rely on what they say. Okay. So instead of taking a majority vote, if I actually have access to these row values, then maybe I shouldn't be taking majority vote. Maybe I should be taking a weighted vote, meaning that I'm going to like weight the response of these people because not all of them are experts. And based on weighting the responses, then I'm going to try to come up with a policy that is based on the expertise. Okay, so if I do that, I can kind of like realize that the expertise of my expert is 1, and that is greater than even the sum of the expertise of all my other agents. So I should just really like rely on what my expert is saying. And if I do that, well, I'm going to correctly identify that this is a black circle, and the correct action here is to say, well, it is black. And again, the reason for that is that the expertise weight for that is much higher. It's like even higher than some of whatever everyone else is saying. Okay. All right, so this makes sense, right? Like, so basically all we are saying here is that if I have access to the true expertise, great, I can do a weighted vote. And based on that, I would be able to have a policy. But in practice, I don't have access to rows, right? Like that is the problem. The problem is that I'm given this data set. I don't even know what the expertise of these agents are. And the question is, what should I do now that I don't even know what their expertise is? So the idea here is actually very simple. So what we are doing here is that if I don't know what the expertise is, I can just assume like that I'm going to uniformly weigh everyone's answer, kind of like take majority vote. And if I take majority vote, then I'm going to incorrectly realize that think that it is a brown circle, like this last one is a brown circle. But that is fine, right? The reason that is fine is that now that I can do this is my policy. My policy is incorrect. What I can do is I can go ahead and update my estimate of what these rows are based on the current status of the policy. Okay? So given this policy, right? Like I think this is the policy. I'm just doing majority vote. What I'm going to do is I'm going to go back to each one of these players. Maybe I'll look at the novice player. And it would be like, well, how many of these did you get right? And the novice player, the only thing the novice player has got right with the majority vote is this last bit, the fact that the novice player thinks it's the brown circle. So I'm going to go ahead and update the expertise and say, well, the expertise of this novice player is 20%. And I'm going to keep updating my expertise. Okay? So basically all I'm showing here is kind of like this bi-level optimization approach where we have a policy. That policy is incorrect based on our original estimate of rows. And then based on that, we are going to go ahead and update our expertise. And our expertise is not accurate right now. But what we can do is then we can go ahead and do a weighted vote based on based on the updated expertise. And based on that, we are able to identify that this is actually black because we are going to rely on the expert solution, who we think is only 80% expert. But then again, we are going to go and update and realize that our expertise values are actually incorrect and fix that. So this was kind of like a very abstract example. I just wanted to talk about this abstract example as a way of kind of thinking about the problem in the most simplest form. So I've also simplified things a little bit too much, but let's just talk about the key idea here. So what is the key idea? The key idea is that we are doing imitation learning, and imitation learning should account for the varying levels of suboptimality that we have in large offline data sets. And the key insight is that the way we are doing that is by leveraging information about the demonstrator identity. So the fact that I know who the demonstration is coming from, which is not a big assumption. Like I can assume that I know like which particular like demonstrator or which particular agent this particular data is coming from. Given that, I would be able to identify the suboptimalities of the agents and go based on that. So as I mentioned, I've simplified things a little bit. So one other point that I tried to make earlier is that this expertise, it's not just a number, right? You can think of this expertise to be state dependent. And in this particular case, right, like I have squares and I have circles. And if you look at this particular intermediate player, this particular intermediate player is actually really good at identifying colors when it comes to the square, but is not very good at doing it when it comes to the circles. So I can make this expertise to be something that is state dependent. And based on my knowledge of the state, or based on my knowledge of the task, I can have a vector that identifies like what the expertise is for a particular skill or for a particular task that we are looking at. All right, so how do we identify tasks? So I've been kind of like talking about the fact that the expertise is also dependent on task. So the way we are looking at tasks is using this idea of task embeddings, which is a fairly popular idea. So it's not like something that we have come up with in any ways. But the idea is we can think about defining the expertise when we have multiple tasks and have a task embedding that tries to identify what are the core skills or core tasks that we should be looking at. So for example, in the setup, we might have a task of identifying a color. So it could be red, brown, or black. Maybe it's going from easy to hard. But we could also have another task that tries to like look at the shape. And maybe the shapes are going to be circle, triangle, and square from easy to hard again. So I have a space of these embeddings of different tasks that I have. And the way I get these embeddings, these task embeddings, is by having a function that takes a state and outputs a d-dimensional vector from that state that tries to capture the skills, the number of skills or tasks that I should be caring about here. So for example, here I could take a red square, right? Like me, and that red square is going to be the state, and passing it through a task embedding is going to give me a vector that tells me how much I should care about color and how much I should care about shape, right? And in this particular case, for a red square, for that particular state, this item, the state being a square, is difficult, right? So that is why the value for shape is higher than the color, which is like on the easier end of things. So it is red, it's easier, so it's at 0.2. So this is kind of, again, an abstract example here. I can pick a brown triangle, and like maybe a brown triangle has a fairly similar shape and color like elements in its vector. Okay, so now that we have task embeddings, again, what are task embeddings? These are functions parameterized by phi over states that tell us how relevant each skill is. So if I have the task embeddings, I can start talking about how much this particular expert is good at a particular task. So I'm going to define this proficiency vector. So this is kind of like a vector, and each element of it is a scalar that tells us how good are you in this particular task. So it's a d-dimensional vector, same size as our task embedding, and it tells us how proficient someone is in each one of these skills. So the reason I'm defining these two is that I can go ahead and go back to my definition of expertise. So far, I've been talking about expertise as a single number, but I can start like modeling what expertise is. And the way I model expertise is to take the inner product of task embedding and proficiency vector to think about how aligned they are. And I would take a sigmoid on top of it to just give me a probability of success. So if you remember, I was referring to expertise as probability of being successful. Are you like 100%? Like, do you have expertise of 1? Are you proficient at this? Or do you have expertise of closer to 0? And that is what the sigmoid basically does. So the idea is that if my task embedding and my proficiency vector, if they're correlated, then that inner product is fairly high. And then if I take a sigmoid on top of that, I'm going to get an expertise of close to 1. And then otherwise, if they're not correlated, that inner product is going to be highly negative, meaning that my row vector, my expertise value is going to be closer to 0.
Sorry to interrupt.
Yeah, go ahead.
Is there any ground truth in this, or is it all with respect to majority?
Yeah, so that's a good question. So at the beginning, I was showing a setting where there was a ground truth row, right? But now I'm saying there is no ground truth in this, right? I'm not assuming that I have access to the ground truth expertise in any ways. And basically, I want to estimate expertise and policy at the same time.
No, I mean, how do you know if? So in the previous example that you had,
yeah,
when you were updating the expertise parameter, you were checking that based on the majority. So if the majority said it's black and this guy said it's brown, then
yeah, that was the first run of it, right?
But then are we still doing that, or are we executing the policy and seeing, oh, it succeeded, so now I go back and update the expertise?
Second one. So basically, yeah, first round, you do majority votes. That's like, because you don't know anything. You assume rows are uniform across all the agents. But then, like, you can think about the next update being updated. Like, you're not going to do majority vote anymore. You're going to use the weights that you think the agents are following right now. And then you're.
So I guess if you can go forward on your slides.
I think it was actually this slide before this. We're talking about this slide, I think.
So it's the one that you updated and figured that the novice one is 0.2, because the majority was saying that it's brown. Yeah, this one. Yeah, so the majority says it's brown. Yeah. And this novice player also says it's brown. Yeah. So you assume that, okay, so this guy got 2%, sorry. Yeah,
0.2. Yeah.
0.2, correct. Where in reality, it actually was black. So he got none of it correct.
He got, well, yeah, in reality, yeah. So that's why this guy is off, right? Like, I think that this person is like 20% right, but that's my current estimate, which is not the correct estimate. So next run, right? Like next run, I'm going to use these estimates, assuming that these are the right estimates. And assuming these are the right estimates, I'm going to go ahead and update my policy. I'm not going to do majority vote anymore. I'm going to weight everything based on that. So for this last element, I'm going to say, well, 20%, this novice was kind of right 20% of the times. So I'm going to multiply this by 20%, like the fact that they're saying it's brown, by 20%. I'm going to multiply this by 40%, by 60%, by 80%. Well, actually, that is going to give me that this particular item is going to be black, because I already think this expert player is at 80% correct.
Right, but then all of this is based on the assumption the majority is always correct, because you're not actually looking at the color, right? You're always testing this with majority. And the underlying assumption is that the majority is always correct. Now, even when you're updating your weights, that's the assumption. I mean, you're again comparing that again with the majority.
I see what you're talking about. So you're talking about what are the assumptions for this to actually work, which I haven't really talked about. Yeah. So you're not talking about what the algorithm does, like you get like what the algorithm does. What you're asking is, when does this work? Like, what are the assumptions we are making, right? The assumption that we are making, I'll talk about that a little bit later. It's actually not that majority is always right. The assumption here is that the suboptimality of agents. So the assumption is that you're going to do the optimal action, like my agents are going to take the optimal action with their expertise level. And then when they are not taking the optimal action, they're taking uniformly bad actions. Like let's say that there is the optimal action of choosing like black here, right? So that is the optimal action of choosing black here. If you are an expert, you're going to choose that black with your expertise. But if you end up choosing any other color, you're going to be uniformly picking any of those bad colors. That is the assumption that the model is making. Let me come back to that. I have a slide on that a little bit later. I'll come back to that.
Sure. Okay.
This wouldn't work in settings where you have adversarial agents, for example, right? Like if someone is like adversarial, this actually would not work. But the assumption is something that's a little more subtle. All right. So so we talked about task embeddings, and then we talked about, okay, yeah. So we were, let me go over this again. So what we are talking about here is that, well, we have task embeddings, we have given states, right? Given a particular state, then you can talk about how relevant the state is by the task embedding. And I don't know what these fees are, so hopefully I'll try to learn them as well. And then I also would like to have a proficiency vector that tells me how proficient someone is in a particular skill. And together, these two are going to tell me like what my expertise is. So we went over this, and we defined expertise to be sigmoid of the inner product of F by the proficiency vector. All right, so now like it comes to the modeling phase. And this is a part that we are deciding on this model. There is no reason for the data to look like this, but this is kind of a modeling assumption that we are making in the case of discrete actions. So the assumption here is that if I have, let's say, 3 agents like pi1 who are following policy pi1, pi2, pi3, they're going to have a proficiency of omega1, omega2, and omega3. Again, I've defined expertise to be sigmoid of the inner product of the task embedding by proficiency vector. And the assumption that we are making is that the policy of each one of these agents, the policy that each one of these agents are following, is going to be taking the correct action with probability of expertise, like whatever your expertise is. If you're an expert, you're always going to take the correct action. If you're 50% expert, you're going to 50% of the times take the correct action. And then in the case of taking an incorrect action, you're going to uniformly choose any bad actions. So I'm not assuming that when you're not an expert, you're going to always like go and pick like the most adversarial thing. I'm actually making an assumption about what you do when you're not an expert. I'm assuming that you're uniformly picking anything else. So that is kind of like the core assumption that goes into play here in the discrete case. Does that, hopefully that makes sense. All right, so that was a discrete case. And so again, just to talk about that one more time, right? Like, so in the discrete case, I'm going to have a policy, and I'm going to assume that I have like noisy agents. And what do these noisy agents do? I'm going to assume that they're going to take the optimal thing by probability of their expertise, which I have defined by proficiency vector and task embedding. And at other times, they're going to uniformly pick a bad action, a suboptimal action. And I'm not differentiating between these different levels of suboptimality. This is in the discrete case. We also have like the continuous case in our experiments where in general, right, like you might have agents who are taking continuous actions. And there's kind of like an analog of this in the continuous case as well. So in the continuous case, you're going to have a set of policies, and then we are going to talk about noisy agents against suboptimal agents, following a policy that is a Gaussian mixture model. And that Gaussian mixture model is going to have some mean and some variance. And what we are doing is we are scaling that variance by this rho. So basically by this expertise. So basically your lack of expertise is going, if rho, imagine if rho is 1, you're going to be expertly following the optimal policy. If rho is 0, you're going to take a uniform action. So that is like what rho does. Like it kind of like does a scaling of the variance of this Gaussian mixture model. So it's kind of like analog of discrete. I just wanted to like have an aside where I talk about the continuous case as well. All right, so then what does the algorithm do? Well, the algorithm does something fairly simple. So basically the algorithm, we're calling it imitation learning by estimating the expertise of demonstrators or IOE. And what it does is it looks at the likelihood of the data set given our demonstrator model. And this demonstrator model is the thing that we are creating here. Like that is kind of like the key idea. That is based on the expertise, which is again, based on the proficiency vector and based on the task embedding. And what we're saying is that you can define a loss function, which is basically the expected log likelihood of your data set. You have a data set of agents coming with different policies. You can look at the likelihood of that data set, given that you assume your agents are following this particular probability, like this particular actions probabilistically. And then this loss function is parameterized by three things. It's parameterized by theta, which is parameters of your policy, parameterized by phi, which is your task embedding parameters. So we need to learn those task embeddings as well. And it's also parameterized by omega, which is your expertise, like your proficiency. Like I'm referring to rho as expertise. So it's like your proficiency for each one of those tasks. Okay. And we're just optimizing basically this loss function. So pictorially, you can think about the fact that you have access to state and you have access to actions. Like these are things that you're observing from your data set. Based on the state, you want to pass that state to a task embedding. And then in addition to that, you would like to learn, like you don't observe this, you would like to learn the proficiency vector, how proficient your agent is in each one of these each one of these skills. I here is for each one of the agents. So this is an index of agent. Omega here is a vector, right? So omega I is actually a vector. So together, this is going to give me what rho is. Remember, rho is the inner product, sigmoid of inner product of F and omega. And then I also would like to find my policy. So policy is parameterized to pi theta. It's trying to approximate the optimal policy that I should be doing in a given state. So given these all together, what I can do is I can use this model of actions that I've been talking about, and I can try to optimize this loss function that I've been discussing, this expected loss of my likelihood, the log likelihood of seeing the particular data, and then I can back propagate and try to get my data. So the algorithm is not doing anything simple. The kind of key idea here is this particular modeling paradigm that we are using here for how to model suboptimality of agents. And again, there's an assumption that goes into play here. So just to summarize, right, what am I talking about? Well, what I've talked about is that given a mixture of demonstrators with varying levels of expertise, ILEAD is trying to maximize the joint likelihood of the policy and expertise, which is again parameterized by task embedding and proficiency vector. And it's making these assumptions about how the agent, what is the suboptimality of the agents. Yeah, so I had a few other slides, which I think are coming later. Let me talk about some experiments, and maybe I'll talk about some of the limitations after the experiments. So we've ran this across a number of domains. The first domain is using synthetic data, and then the other two domains is actually using human data. So let's look at the first domain. So this is a fairly simple domain. It's a mini grid environment where we have this empty grid, where we have an agent, the red agent who has partial observability. There is a goal state, that's a green state, it needs to reach that. And then you have other versions of it where you have maybe lava, or you have moving obstacles, or we have this sparse reward situation where you need to grab a key and then open the door and get to the other side. Here are some expert rollouts of how an expert could play some of these tasks. This is coming from pre-trained policies through reinforcement learning. So you could kind of get these agents do various types of tasks. So what we're doing is, again, this is synthetically generated data, so we can kind of make it so it works with our setting. But I just want to show some proof of concept here in this environment. So here we're adding uniform noise to this data set that we have been looking at. And we have kind of a variety of combinations where we are looking at 10 different agents. And these 10 different agents, they could be all noisy and one expert, or we can have other variations of it. For example, we can have 5 noisy agents and 5 experts, or all experts, or a setting where the expertise goes up. So this is what I'm showing here pictorially, what rho actually means. So I have 10 agents, varying levels of noise. What I'm comparing here is I'm just going to show the empty environment and the obstacle environment just to prove a point. So the empty environment is really simple. Everything should really work well on it. And we are comparing behavioral cloning and generative adversarial imitation learning with ILEAD. One note is that Gale actually has access to dynamics as well. So the Gale approach usually needs to do reinforcement learning within itself. So because of that, it needs to have access to the dynamics of the environment. But ILEAD is not making any of those assumptions. So we're not really assuming that you have access to rewards or rollouts in any sense. And then the obstacle environment is slightly harder. So here, as you can see in the empty environment, everything is doing really well. Of course, ILEAD is also doing really well because it's just a simple environment. But then when we start making the environment slightly harder, then some of the other approaches start failing. And ILEAD is going to actually outperform these approaches because it does consider this expertise level and uses that for its planning. So kind of the key point that this was showing is that, well, we could identify which experts are good and actually use that expertise signal to learn a better policy. But so far, I haven't shown any task embedding. So what we decided to do was we decided to actually consider this notion of having task embeddings a little bit more in this environment. So the idea is that instead of just saying, oh, we have experts in all tasks, what we can do is we can train agents that are good at specific tasks. I can have an expert who is good at solving the empty task, or I can have an expert who is good at solving the lava task, and so on. So the idea is that we have these agents who have full expertise in a particular task, and then they can act noisily in other tasks. So this is how I'm showing the data set here. So for example, let's pick the lava expert. So the lava expert is really good at the lava task, and the gray the gray data is showing that they are noisy in all the other tasks. So that's how I'm showing the data. So let's look at how this works. So what I can do is, again, I can have everyone to be an expert. If everyone is an expert, ILEAD or the other methods here are behavior cloning on all the demonstrations or behavior cloning on the best demonstrator. They're also performing really well. But this beta parameter is basically varying the expertise of adding noise, basically, varying the expertise of the agents in the other tasks that they're not an expert in. So as you decrease beta, you're starting to see that, well, these other methods are not going to work really well. But then again, ILEAD is able to even work at 70% success, even when beta is 1%. So even if my agents have only 1% correct actions, in these other actions, we are able to in these other tasks, we are able to get a 70% success rate as opposed to 40%, which is what we see with the other methods. And here are some rollouts. So kind of the quick summary for this mini grid environment is that we can have this method that can look at states and then actually correctly learn the task embedding of those states and use a state dependent expertise measure to learn a better policy and actually be able to tap into these suboptimal data. But so far, what I have shown is made up data, and that made up data can fit my model really nicely. So what I want to show next is basically these two domains where we are looking at collected data sets by other groups. These are human data sets, and we're basically trying to show that this idea actually works well when we are using these collected human data sets as well. So the first data set I'm going to talk about is this RoboMimic data set, which is from Stanford Vision Lab. I think it just came out this past quarter. And it is basically 50 demonstrations from 6 humans. I think each one of them are giving 50 demonstrations. And these 6 humans, 2 of them are what they call worse agents, 2 of them are okay agents, and 2 of them are better agents. So if you look at, basically this is teleoperated data. So the worse agent doesn't have as much success in doing the task. Okay agents are slightly better. And then again, the better agents are a lot better. And again, this is actual human data. These bucketings and clusterings are done by the authors of RoboMimic. So we don't really have we don't really know quantitatively, right? How much these agents are better than each other, based on the data set. This is just what is given. So what we are looking at is we are trying to compare iLead with two very strong baselines that are actually coming from the RoboMimic data set. So the first baseline is PCRNN. So this is behavior cloning, but adding an RNN like component to it to try to keep track of history. And then Iris is an offline RL algorithm. So the point of RoboMimic data, like RoboMimic paper and data set, one of the points was trying to compare imitation learning with offline RL. But like here, we are kind of in the imitation learning realm of things, and we're just trying to show how you could learn from suboptimal demonstrations. And for example, when you're using all of the data, BCRNN is a very good baseline actually, and iLead is performing very similarly. But when you start looking at like some part of the data that is actually not as optimal, so you have some of these worse behaviors or okay behaviors or a combination of them, then we can start seeing iLead actually outperforming BCRNN and Iris, which is kind of nice because like it actually like captures that suboptimality. Let me show you some rollouts of this. So this is a rollout of iLead looking at the setting where you're using all of the data set when you have 78% success. And then even in some of the other settings, right, like when we're using the worst data, so this is data from like 2 people who are not good at this, we're still getting a fairly like okay, like I don't know, 46%, fairly okay success rate, at least like compared to some of the other methods. All
right. Quick question. Yeah, so I mean, correct me if I'm wrong, but basically the way I understand this is actually making progress is essentially by recognizing, identifying expertise by assuming that, well, if I see randomness, then that's not expertise. And if I see someone behaving non-randomly, then it's expertise. But I guess obviously there is biases, and you can have agents who just, in a consistent way make mistakes. And then that you wouldn't be able to distinguish that with this approach. Is that right?
So there are kind of 2 points. I would say the big insight, or the insight that helps this to actually work, is the fact that your data is coming from a particular user, right? Like going back here, like if I know my data is coming from this particular user, and if I realize that this data is not very consistent with other data, and other data is making me like actually like do the task better, but like I keep like saying that this data is not being consistent, like the fact that I can identify that it is coming from a particular user, then I can go ahead and update the expertise of this agent and be like, well, I'm not going to trust this agent. So I would say that is the insight. But again, like there's this question of what is the assumption here? If these agents were adversarial, would this work? And I would say, well, it wouldn't, right? Like it actually like wouldn't. If all of these agents were adversarial, they wouldn't. The assumption here is that when these agents are suboptimal, they're uniformly picking bad actions. They're uniformly bad across all other options that they could, all other actions that they can give. So that is kind of like the assumption that allows this to make progress. So it's not like
so you're also assuming that you getting a signal whether there was a success or not for the task in the end.
Yeah, in some sense, right?
Okay,
like,
yeah, because that wasn't clear to me. Okay.
Yeah, sorry about that. Yeah, new talk. Still getting the kind of like figuring out what is the right way of presenting it. Yeah, but that's kind of like, yeah, the key idea that you are getting some signal, like even if people are wrong, and that signal is like, yeah, like it wouldn't work if, again, these agents were adversarial. But I would argue that, again, in most of robotic settings, we are in settings where we have this type of data. Like we have this problem in all of our other domains where we collect data from actual humans, and they are very off from like optimal RL agents. And they're not like that bad, like they're not trying to act adversarially, but they just have like various biases that we need to like understand, and we need to maybe filter out for various types of tasks. So yeah, so like I think and again, like that assumption that I was making, we didn't even verify if like this is empirical. In this RoboMimic data set, we didn't verify that assumption is true or not. Like that assumption that I was making is more on the theory side of things, and actually like proving that we would not do worse than behavioral cloning under that assumption. So we have some theory that I'm not covering here. In the case of real data sets, this RoboMimic data set, like we actually don't know if our assumption is being held or not. Like we are just like using some data set that is out there and running the algorithm on it, and it is performing fairly well. And that kind of gives me some signal that this assumption is not super unrealistic. This is actually like a fair assumption to make about data sets.
Sorry, to just follow up on Christoph's question. So it seems to me that you're actually getting that signal Meaning, like you mentioned that if I have this expert and it's giving me a good policy that can solve the task, so at the end you get to know that the task was solved. Like the maze example that you showed, you know, eventually when you get to the target, you get a reward.
But we don't see the reward in ILE. Like I'm showing the actual value for evaluation, but we are not seeing that as part of the algorithm. Like for example, Iris sees that as part of the algorithm because that's an offline oral algorithm. It actually sees the reward. We're not seeing the reward here. It is, yeah, kind of that assumption that people are not adversarial and they're mostly like giving us correct things. And like I can.
Well, that's the thing. Then how do you know? Let's say, I mean, going back to the example, let's say you have one adult and everybody else is like a year-old kid who are trying to feed themselves, right? Now, let's say you have thousands of these kids and only a single adult, and all the kids are just feeding their hair and their shoulders and their cheeks, and only the adult is eating properly. So if all you're getting is a majority, then you're going to be feeding your chick. And you would never, ever know that, okay, the adult is actually eating properly, right?
Yeah,
how would you know?
So the question is, what is the guarantee? So I've been telling you guys the assumption, right? Like the assumption, again, like the assumption is that you have agents are suboptimal. When they are suboptimal, they're uniformly bad across all actions. Like that is the assumption. But like, what is a guarantee? Like, what does that give me? Like, does that give me that I can always like converge to the best policy? It doesn't. Like the only thing it gives me is that I can be better than behavioral cloning. Like that is like the only thing that it gives me. So I'm not guaranteed that this is going to actually converge to the optimal policy in any ways.
Right. So I mean, with that, we have that guarantee from the multiplicative weight update and expert update literature, right? And it's actually even good with respect to adversaries. So even if you have adversaries in your experts, you at the end you have zero regret. So if you do this multiplicative weight update, which is basically what you're doing, that you're updating the weights on different people, at the end you have zero regret of choosing each one of them, right? You're doing better than every single one of them in hindsight, right? But that the guarantee that you get with that one is if you see the grand truth and then you update your weights with the grand truth. In your case, seems like you're updating it with the majority. So at the end, it seems for this to work and converge to optimal policy, you need the majority to at least do the right thing, right? The majority.
No, I see what you're saying here. How about, okay, let's take this offline because like I understand your point right now and I don't have like a good answer for it right now. So how about, can you send me an email and I'll actually like add like Andy and others to it too.
Yeah, absolutely, sure.
I think that would be really helpful. But yeah, no, I get your point. And yeah, we are not like again, like empirical, I'm showing like a lot of empirical results here. And in these empirical results, actually, where's my cursor? But these are great points that you guys are making. And again, like I wasn't here trying to like make a theoretical statement in any ways. I'm basically talking about a very empirical like robotics setting that I think is pretty interesting. And I'm basically saying these assumptions that you can make here are pretty like practical, like even like when you're relying on kind of like these large offline data sets, and it outperforms like state of the art, like offline RL and BCRNN, which is kind of the state of the art of what people do like in these types of domains. So I'm not really like here trying to like prove a theorem or like make a theoretical statement. I'm like basically like saying this, like even if you don't have access to that signal, which is a big assumption to make, you could do fairly well when you're thinking about these realistic data sets. I think it would be interesting to try to talk about it like more from a theoretical perspective as well. And again, like happy to chat about it offline as well. So I'm like running out of time a little bit. So let me skip this. But basically like another like realistic example is you could look at chess data sets. So we looked at this Lichess chess database of actual like chess playing data. And here we have ground truth data. Here we actually like have ground truth data of like ELO rating of these different chess players. And we've been looking at kind of like chess end games. And we show that if you pick like chess end games, using these chess end games, like you could actually like identify these expertise and like basically this algorithm is able to capture the expertise of the agents. I think this, I've already kind of like talked about it a little bit. So let me kind of, given I have 10 minutes, I'd like to talk a little bit about this idea of play too, given the time. Yeah, so kind of the key takeaways here is that, yeah, in practice, right, like we have data that is collected from multiple demonstrators with varying unknown levels of expertise. And what we are doing here is we are able to like capture these state-dependent expertise, like learn the state embedding in addition to the policy. And that allows us to actually tap into some of these real data sets and be able to identify expertise in those settings. So let me talk a little bit about play and some of the work that we are doing in play and some of the effects of that, and maybe I'll wrap up then. So why do we care about play? Because, well, in practice, right, like when you're thinking about these robotics data sets, again, we are thinking about learning generalizable like multitask policies from humans, and collecting data can be difficult. So for example, if you want to have a data set that like moves this object around, like pushes it right, forward, lift, and so on, in these settings, right, it's actually pretty unscalable to do that. Well, what is the reason? Because it's expensive to collect data because you need to usually write out the task specification, like what the reward is. If you have worked with any of these systems, like if you want to do any simple like pick and place task, writing the reward function requires like a week of figuring out what is the right reward shaping metrics to get that right. And then you also need to reset after every demonstration, right? Like if you actually have like a real robotics domain, like resetting requires a lot of it takes a lot of effort. So in general, that makes learning from demonstration pretty unscalable. So like it's expensive to collect data. It's expensive to design these settings. In addition to that, it'll have generalization issues too, right? Like for a lot of these demonstration settings, the start and goal states are predefined. And then we have kind of like a very limited state action coverage. So generalization ends up being a problem too. But it turns out that play seems to have a lot of promise here. So human play, it's unstructured, undirected, multitask demonstrations. It ends up being very cheap to collect. So that addresses the scalability issue that we've been talking about. Because you don't need to have any task specifications. You can just have undirected movements like in this environment. It's reset free. You can continue wherever you have left off. You don't need to reset the environment. And that kind of, again, like all of that helps with the fact that this is cheap to collect, and that helps scalability. And we also get quite a bit of state action coverage, and that helps with the generalizability side of things. And also, if you look at play data, it gives you access to human priors on goals and behaviors, and that can be really powerful. So there was this work at Coral 2020 by Corey Lynch and others, and they were looking at play data. And here's a plot from their work where they were talking about state action coverage when you're using play data as opposed to other types of data like expert demonstrations or random actions. And the plot just gets like worse when you look at 8 hours of data. By worse, I mean like it becomes more dramatic if you start thinking about state action coverage that you would get from play. So again, lots of promise here. If you think about imitation learning policies that are learned from play, they can be more robust because you can have a lot, like a much better coverage of state and actions. And that is in general something that we are interested in. So then the question is, well, how can we learn from play data? Like how do prior work address this idea of learning from play data? Of course, like there's this, as I mentioned, there's this work in Coral 2020 that takes a particular approach for learning from play data. What they look at is they look at these things that are called latent modal plans. So basically the key idea of that is that you can take a sequence of data, a random sequence of data, and you can learn plans that represent these random sequences from play. So you can basically take a sequence, let's call that tau. It has some start location and some end location of the object. I'm going to refer to that as OH. So that refers to like where the object ends up at. And from that, we would like to be able to learn a policy that we could kind of run in practice. So what this work does, I'm going to briefly mention that because our work basically like built on top of it. Basically, what this work does is it tries to train a number of networks. So first off, it looks at the trajectory, and it trains a posterior network that takes this trajectory, this sequence, and tries to like basically get a plan out of that. Let's call that Z. And then it also at the same time trains a prior network. The prior network doesn't have access to tau. And it takes the initial state and the final location of the object, and it gets Z prime, like it tries to like get Z prime, which is a plan, and that we try to match as closely as possible to the posterior. So there's a KL divergence loss here that goes on. And then I can treat this plan that I'm getting from the posterior, I can treat this encoder as kind of like an encoder-decoder architecture, where I also have like, I also can train a policy that samples from the plans that I've got, and then I can try to reconstruct my actions as closely as possible. So there are kind of like three components that go in here, right? Like I have this encoder-decoder structure where the encoder gets the play data, tries to extract a plan. I pass that plan into my policy, in addition to states and maybe final goals that I want to get. And I try to get actions, and I have a reconstruction loss that tries to match that as closely as possible to my observations. In addition to that, I can also have this prior network that tries to match the posterior network as closely as possible. The reason I need the prior network is that during test time, I don't have trajectories, so I can't really rely on this posterior. During test time, all I'm using is the prior network and the policy. So during test time, I'm in a new state, I have a goal state, and what I want to do is I want to actually be able to get to that goal state. So my posterior goes away, that is not useful anymore. And what I have is like, I actually have like this goal state, and I can basically get a plan out of my prior, pass that plan to my policy, and try to get an action out of that. So that is kind of like the key idea that goes into learning from play. So that's all great, but like one big assumption that this work usually makes is that it kind of like picks basically these short horizon windows, and these windows are typically short fixed horizon windows, like 1 to 2 seconds. And you might imagine that having a short fixed horizon window of 1 to 2 seconds is just going to fail in many settings. And part of the reason is that like a lot of tasks can be longer than 1 to 2 seconds. Sometimes multiple tasks happen in 1 to 2 seconds. And you don't really get the right correspondence between these trajectories and the goal that you want to achieve. So this is kind of the part that I want to skip given the time. But there are actually like a number of reasons that this type of approach fails. Like one of them is selecting the horizon length can be task specific. I'm giving some example. Let me skip a couple of these. Yeah, so kind of like the key reasons that play LMP like fails like just off the shelf is that selecting these horizon length, they're often task specific. Depending on the task, you might have different size of horizons. And then if you have these fixed horizons, you might attribute like wrong goals to specific behaviors. And in addition to that, like when you pick like these fixed horizons, what happens is that you think that is equally important to any other fixed horizon length, like trajectory. But some trajectories are more important than others for the type of task that you want to do. So instead, the key idea, the key insight here is something that's very simple. It's basically viewing play as object interactions. So what we are doing is basically we think of play as this consistent back-to-back environment interactions, but it actually does have a number of phases. It has like a pre-interaction phase where the robot gets to the object. It has an interaction phase where the robot actually makes contact with the object and pushes the object, let's say, or influences the object. And there's a post-interaction phase, maybe when the robot retreats, and maybe when the object like slides still, or like there's gravity still like acting on the object. So that's kind of like the post-interaction where the robot is not influencing the object, but the object may be still being influenced by the environment. So the key idea is if we segment our play data into like these different phases based on object interactions, we can potentially sample more informative and accurate goals, and we can bias the latent space to model the interactions rather than some random sequence. So that's kind of the key idea. Again, given the time, I should probably skip all of these. Basically, like, let me maybe talk about the idea of affordances. So basically, like the idea here is that we only look at the interaction phase as a way of learning that plan. And I'm referring to that plan as an affordance. So an affordance is a property of an object that defines how it can be used, right? So in this case, when we are pushing, one would say like the block affords the pushing motion. And that is kind of like the affordance that we could potentially learn by just focusing on the interaction phase. So that is literally like the key idea. And like this algorithm Plato learns latent representations of affordances from this interaction period and uses that as a way of like basically like you would be able to identify these different affordances like pushing, lifting, and so on, but only focusing on that region and then planning based on a goal state that comes from a post-interaction region. And I'll skip the details, and that kind of addresses all these issues that we were talking about. So Plato like considers like variable length horizons, and it can potentially consider long horizon sequences depending on the task, depending on the particular affordance and the particular sequence of contacts that you're making with the object. And in general, taking this object-centric view can lead to more informative and consistent goals. And basically this latent space ends up capturing object affordances rather than some random like place sequence that you might get without thinking about object sequences. So basically, maybe I'll skip this one too. Basically, we have evaluated this on a number of domains. Again, it's a very simple idea, but it like heavily outperforms like previous works like PlayLMP in a number of domains. We also looked at actual human play data. One thing that was interesting with actual human play data as opposed to synthetic human play, which is like what you see in the top rows, it is harder to get things working with actual human play data. And our architecture is actually slightly different with actual human data. Like we have like, we needed to do quite a bit of hyperparameter tuning to get things working with real human data. And part of the reason is human play data is a lot more variable than synthetically generated data, which I think in general is an interesting point to think about. Because again, we make these algorithms making this assumption that, oh, it's going to work great when we get like our human data, but it doesn't. And I think it makes sense to think about what are the inductive biases that are present in the human data that could potentially make these harder. And we have looked at kind of like some 3D environments, all in simulation, because again, collecting like play data can be difficult on real robots as well. But yeah, we are looking at a number of environments, looking at a number of primitives like lifting and pushing and rotating. And in all of these domains, again, the algorithm is outperforming previous techniques. Yeah. Okay, all right. So given that, I don't think I'm going to talk about learning from comparisons. I'm going to just try to wrap up and just like wrap up some thoughts here. So what I've talked about today is that maybe we should stop like worrying so much about expert demonstrations and learning from expert demonstrations. And maybe we should try to tap into like some of these other sources of data, including like maybe mixture of demonstrations with varying levels of expertise or learning from play. And I didn't get a chance to talk about comparisons, but you can also think about pairwise comparisons and how pairwise comparisons between different control strategies could potentially lead to learning reward functions or policies that are useful for robotics agents. I also didn't get a chance to go back and talk about the feeding project. So you might ask, okay, you started with the feeding project, like how is that going? And like I would like on the honest side of things, like, it's still like pretty difficult to use like ideas around learning in this domain. And like we are currently at the stage of like trying to like pick up food, and it has quite a bit of failures when you're thinking about picking up food with various shapes and various like softness. And like thinking about different types of scooping strategies tends to be pretty difficult. I think it would be interesting to try to learn from actual human demonstrations, including suboptimal demonstrations, but I think we are far from that, both in the sense of byte acquisition, and also we are looking at transfer, which tends to be a pretty difficult task as well. So thinking about like forces that we put in and so on, like these are right now mostly like planning-based policies that are not using any learning or any data. But I think it would be interesting to look at that as part of future work. So with that, I'd like to thank the group during the COVID time. This is a hike that we did over the summer. And thank you guys. And yeah, I can take questions.
Great, yeah. Thank you very much for the talk. That was excellent. I think we already had some questions, obviously, in the talk. I don't know if there are other questions. You can just unmute and ask.
So
right,
yes,
well,
I have a question.
Oh,
Yeah,
sorry,
go ahead, Christoph. Go ahead.
Oh, that's fine. Yeah, I guess I have a follow-up question to the first part of the talk. Apart from so you have this assumption with non-experts behave randomly, like uniformly randomly, which we talked that if there is biases in how you make mistakes, that can be a problem. But also, what if you have tasks where there is many optimal ways of achieving, but very different ways of achieving a goal, and then you have this type of hybrid demonstration data. Well, how would you deal with that?
Yeah, no, that's a good question. And in general, right, like I think that in that case, the policy class should be more expressive and be able to like quality of data. So something that in the different work, for example, we were looking at in terms of learning from pairwise comparisons and rankings, like we are thinking about kind of like a multimodal representation of the policy and being able to learn that multimodality. But in practice, if you don't have that, right, like it ends up making things pretty difficult. This is something that we observed in the play data. Again, like in the play data, it's just like pushing and pulling. Like it's very simple. Like how much variability do we think we're going to have? But we collected actual human data, and it turns out that people have very different, and these people are graduate students, not random people. Graduate students working on the project have different ways of like pushing, and even like that variability needs a lot more expressive like model. So like we increase the model size to be able to capture that multimodality in the play work. But yeah, if we know what form it is and all that, I think like using those inductive biases can potentially help. I think having like a more expressive policy class could potentially handle that.
All right, thanks, good. Thank you.
Maybe Pascal, do you want to ask a question now?
Sure. Yeah. So the second part, is it fair to say that with the learning from play data, we're mostly learning a model of the environment, and then essentially we just get to have like a better model based on which we can do planning faster?
I think that's a fair way of thinking about it. So with the play data, you have a lot more coverage. I think that is one of the key things that it is going to give us. And because we have a lot more coverage, then we can put less budget on exploration, or we can put like less budget on like figuring things out, because like that gives us already quite a bit of data. I would say that is one of the benefits. So that helps with generalization, one of the main benefits. The other benefit is it's easier to collect as well, right? Like you can just like have like people like move things, and you don't need to reset. You don't need to like think about like goals and like getting a policy that actually does the task right. But I do think the core benefit is that fact that you have a better coverage that gives better generalization.
Okay. And then in the first part, I think I saw that you had one slide that I think you didn't have time to cover. That was asking the question of, can we learn better policies than I guess the experts in the data. So I was going to ask that question, but you had that slide, and then I don't recall that you really went into detail. So I was wondering if you could elaborate on that.
Sorry, so the question is like better than...
I guess the question is, okay, you're doing imitation learning. Typically in imitation learning, you just get to imitate policies the way they are, and then if you don't have good policies, then to beat them, usually you can't do that. But I was wondering, in your framework, if it is possible to actually go beyond and end up with a policy that's better than any of the experts that are part of the data.
Yeah, that's a good question too. We don't have again any guarantees on that, so I'm just like speculating when I'm thinking about giving this answer. I think actually, like I think empirically we were able to, so okay, so here's actually so for example, like we had a setting, let's say that you have an agent who is good at like the Lava task, and you have an agent who is good at unlock task, and you like their suboptimalities are covering different parts of the state. You can have an agent that becomes better than both of them because it like realizes that one of them is like expert in one task and one of them is an expert in another task, so it can become better than both of them in some sense. Because if it correctly identifies the suboptimality, it can become better at both of the tasks. That is something that we empirically saw in the mini grid environment. Again, like how would you formalize that effectively? I think you want to like talk about like having again a good state coverage by your experts, which we haven't formalized.
Yeah. Okay. That makes sense. Thank you.
Any other questions? Maybe just briefly on my own thoughts. So like when Syed was asking about this, that update, like I thought that slide was really neat. And you're showing how this sort of method updates iteratively. And it does look a lot or similar in some ways to this multiplicative weights update procedure. And so I think like, it would be interesting to know, maybe it's not something you're interested in, but for someone to search out or to like try and understand like under what conditions does this thing converge? Because
that would be interesting.
There's probably some, precise set of conditions that might not be it might not actually require this uniformity over all the other choices, but maybe something slightly, more relaxed than that. They can't be adversarial, but there's some other conditions.
Yeah, I agree. That would be interesting. Yeah. So like, we didn't really like explore that to like a deep extent in any ways, right? Like the only exploration that we have is under this particular assumption, right? Like this is a model that we have, which makes sense, like given the data sets that like we observe. And like the only thing that we can say is that, well, it's going to be like better than like, it's not going to be worse than behavior cloning, but it's a very weak statement.
Right. Yeah.
And you're right. Yeah, there was quite a bit of work on the ML side of things that tries to like actually like formalize these under maybe like less restrictive assumptions. So I would be actually curious to like see what is I don't have a good answer, but I would be curious to agree on this like myself and see what are kind of like the guarantees here. So I think it was Majid who was asking, right? Like
that's right. Yeah. I don't know if he's still here or not, but maybe he left. Yeah, but anyway, it was really interesting, and I thought you're very, very clear. I think when you present things more clearly, then you get more detailed questions, right? Like if you're you can always I
mean, thank you, but like I think it's good to like actually like get into details of things. Like new work, so it's great to get feedback on like things. This is the first time I'm giving this talk, so
any final questions, or otherwise we'll thank Dorsa one more time.
I just had a comment. Hi, I'm Sirisha. Regarding the framework that you're considering, just your discussion right now, is bounded rationality something which may explain?
That's an interesting question. So we have some work around bounded rationality. I didn't really like talk about it in these settings. You could start thinking about suboptimality of humans being in the category of bounded rationality. And then you can think about like models of that bounded rationality. And if you have those models, then you can have like a lot more structure, and that more structure could potentially help you learn a better policy. I think that would be an interesting direction to explore in this setting here too. We didn't make that assumption because we didn't want to like put extra assumptions like on the data, but we have some work where we are looking at like ideas around bounded rationality and prospect theory for driving in near accident driving scenarios. And like under the structured models, then we can make statements about the human model and like how the autonomous car should plan like close to like the human like driving. So I have some work on that. If you're interested, I think it's an HRI 20 paper.
I'm new to that like area. I wouldn't say I'm in that area at all. But like when we are considering, we don't have to like think about humans being either adversarial or even uniform over the other option. They could just be bounded rational. But I don't know how complex that becomes then.
It doesn't become actually that complex. I think some folks might argue that might not be like, that might be too restrictive to assume.
I see. Okay, got it.
I think that would be interesting. Like, I think it is like a more model-based approach that tries to like come up with a model of what are these suboptimalities. And I think it is true, like looking at this human data, I think it is true that some of it is suboptimality, but some of it is also, or some of it is bounded rationality. But some of it is also things that we don't know how to formalize yet, which I think is a very interesting direction looking at actual human data. There are various types of inductive biases present. Some of them can be explained by bounded rationality. Some of them can't. We oftentimes try to filter that out, and like everyone does it in their project and no one talks about it. But I think we should like talk about like this type of variations that we see in human data a little bit more and think about it more.
Yeah, thank you. Thanks for the great talk. Thanks.
All right, well, why don't we stop there? Yeah, thanks so much. Really appreciate it.
Thanks a lot.
And thanks everyone for joining.